Yeah. Is it working? Some issue.
Yeah, I can't share this. This is not letting me share your screen on Zoom. I'll just shoot this.
How they're going to complain about that, though?
Yeah,
Take your time. It's okay. If we go over, I'm going to. Okay, just a warning, guys. Today's class is, the lecture is kind of long. I'm not going to finish it today. So we will probably go over. And sometime tomorrow, I'm going to get on Zoom and I'm going to finish the lecture. Those of you who can make it must. Those of you who cannot make it can watch the video, number one. Number two, as announced in the, Paul, is it working? Okay. So we're having broadcast issues. So for those of you who watched the logistics video, and I hope all of you have, you know that your laptops are going to be shut in this classroom, except for polls, right? So, may I? The laptops are going to be shut in the classroom except for polls. Your smartphones are off. This is a really dumb classroom. And if you really must work on your laptop, please leave the room. Folks back there. So if you really must work on your laptop, go outside, work outside. Do not stay in the classroom. Do not disturb the people around you. Oh. Okay? All right, you guys at the back, shut your laptops, please. Keep them out because we will have Zoom polls. It's just that, or rather Piazza polls. I just don't want, it's an unfortunate habit. Your generation has a much shorter attention span than mine did, thanks to social media. I have found that if I do not impose these rules on you, 15 minutes into the class, someone's giggling at the back of the class and it's not at my jokes. So we don't want that happening. You lady there, do you mind shutting your laptop?
Yeah, that's my laptop.
Thank you. So, okay. Yes. Pass these out. Here's the second thing you're all going to do. I need to know your names. If nothing, because I need to put a name to the face, right? So each of you is going to get a sheet of this kind. You're going to make a name board. The way you do it, you fold your sheet in half like so, as perfectly as you can. And then you fold each of these halves in turn inwards in half, like so. And so that's actually, you folded it in four. But the nice thing is that now this is going to sit very nicely as a triangle. You write your name on it in big legible characters so that I can see your name from back there. And I need to know who you are, right? Can I begin? Okay, do you have any questions about the topics we've covered so far? Any questions? Come on up front. There's room up front. You sure you're okay? My TAs get very excited to come to class. They tumble down the stairs. But anyways. Aha. You had one ready for me. Perfect. Your name I will remember. How do you pronounce your name? Digan. All right, folks, let's begin. So we're going to continue our series of lectures on learning neural networks. Here's what we've seen so far. Everybody, calm down, please. We posed the problem of training neural networks as empirical risk minimization. So what was this mythical risk that we really wanted to minimize? Thomas, do you remember? divergence, just the divergence?
I don't remember the formula.
Somebody else says, you're halfway there. So maybe, Hadrita, can you tell me what it was we are trying to minimize? We're speaking of empirical risk minimization. What was the risk? Muno, you. We wanted to minimize the shaded area that we showed in the plot. What was that? That was the expected divergence, right? And what was the difference between the expected divergence and the empirical risk? What's your name? The empirical risk is the average taken at a bunch of samples. It's an approximation to the expected divergence, right? That's what we want to minimize. And the hope is that if you minimize it, then if you minimize the empirical risk, the actual expected risk will also be minimized. And basically what you're saying is that if you fit the function at the specific training locations of the training instances, you kind of hope that it fits everywhere else. So this was a problem of function minimization. The loss that we defined was a function of the parameters of the network. And so when you minimize the loss, you're basically performing function minimization. We're going to continue talking about this. First, some notation. We're going to assume that the network is layered. What I mean, as we know, we can always define layers. But when I speak of a layered network, specifically, I'm thinking of the kind of layer networks where all the output neurons are at the same layer. This is not required. This is just for convenience. So we're going to use a notation of this kind. Every neuron has a bunch of incoming weights and has a bias. So the neurons themselves are in layers. For any parameter, you have a superscript. The superscript represents the layer. So B superscript 1 represents the bias of a neuron in the first layer. The 0th layer is the so-called input layer. There are no neurons over here. This is just the input. It's just convention to call it a layer. But the rest of all the remaining layers have neurons. Similarly, if I have a parameter Wij superscript 2, then it means that it's a connection from the ith neuron of the first layer to the jth neuron of the second layer. So the superscript represents the destination layer. And since there are two subscripts, one of them represents the index of the neuron from which the connection is emerging. And the second one is the neuron to which the connection goes. So again, here's how we perform function minimization, if you remember. We use the gradient descent algorithm. So you would initialize the parameters somehow, W subscript 0. Here, without the parentheses, the superscript represents the iteration number. With the parentheses, it represents the layer. I run out of notations, so sometimes you have to overload these things. And can you find the USB jack somewhere? Let's deal with it. Okay, all right. And so, so how did gradient descent work? Can somebody tell me, Shreyas? Why did we move in the opposite direction of the gradient? Pardon me?
Gradient point in the direction of the ascent.
Of the ascent is?
Or of the increase.
Of the steepest ascent, right? So the gradient points in the direction of the steepest ascent. And so that's why we always took a step against it. We kept doing it until, when did we stop?
The gradient is small enough.
Pardon me?
The gradient is small enough, so we consider it as converged.
So will the gradient, is it guaranteed that the gradient will be small?
Well, it depends. Like if we select the wrong learning rate, it might not.
We saw some conditions where, we saw some examples where at the minimum, the gradient was not 0. What was that? Anyone remember, Chetan?
It was like something like
Where, Thomas? Pardon me? No. So we were looking at losses. When we were trying to minimize losses, we said the gradient need not be 0 at the minimum, yes.
Is this the saddle point?
Wasn't the saddle point. We showed that, for for the KL divergence, what was the gradient at the minimum with respect to the output of the network? It is 1, right? The gradient need not go to 0. So when do you stop these iterations? When the values do not change. When basically you've hit some point where any further updates does not really, do not really reduce the loss. So all of this familiar with you folks? Yeah, okay. So here is what the gradient descent rule looks like. We're going to initialize the weights and then keep taking steps against the gradient of the loss with respect to the parameters. But then if you look at it at an individual perspective, from the perspective of individual parameters, we know that the gradient is just a vector comprised of partial derivatives. So for each parameter, the update rule is like this. You're going to take a step against the derivative of the loss with respect to that parameter. Now, there is a very intuitive explanation to this, right? What is this term here telling me, this derivative? This derivative tells me how much does the loss increase if I increase my parameter by a small value. That is the definition of the derivative, right? So if increasing my W a little bit increases the loss, what do I want to do to my W? Increase or decrease it? Decrease it, right? So which is why there's a negative sign. And so that's this, and the magic here now is for us to figure out how to compute this term for every single parameter in the network, right? So what is that term again? Our loss is the average divergence over the training set. So by the rules of derivatives, the derivative of the loss with respect to any parameter is the average of the derivatives of the losses for the individual training instances with respect to that parameter. And so having arrived at that, this means that what we really need to be able to estimate is this guy here, the derivative of the loss for individual training instances with respect to these parameters. If you can compute that, then you can compute the average derivative, you can perform the gradient descent updates. So back to calculus. Now, for any differentiable function, how did we define derivatives? Anybody remember? Yes.
The multiplicative factor, like if you're increasing the input by a certain perturbation, was the multiplying factor increase?
The multiplicative factor by which you multiply the increment in the input to get the corresponding increment in the output. So for any delta x, here I'm assuming scalar y and x, the derivative dy over dx is the term that you multiply delta x by to get the corresponding delta y for a sufficiently small delta x. Now this I can represent, so I'm introducing some notation, some visualization over here. When I say y equals f of x, y depends on x, right? I'm going to represent this using this little graph, which has an x pointing to y. And so this is what I will call an influence diagram. X influences y. Influence diagrams are really nice things when you want to work with derivatives, as you will see. So now this edge is going to have associated with it a weight. And the weight is the derivative of the variable at the output of the edge with respect to the derivative at the input to the edge. So here the output is y, the input is x, the weight is going to be dy over dx. And so correspondingly, for any increment delta x over here, for small enough delta x, this delta x multiplies the edge weight to give you the corresponding delta y. This making sense to everyone? Right, okay. Now, for any differentiable function where y is a function of many variables, x1 through xn, what is the influence diagram for this guy going to be? Assuming that this represents a standard influence diagram for one output variable, which depends on one input variable, how would you draw the influences over here? Anyone? Can you speak up, please?
So you can write the derivative
I'm speaking of the influences, but you're getting there. You're right? So what I can do is just say, here are all the variables, x1, x2, xm, and all of them influence y, right? So again, you get this figure here. Now, if I wanted to compute, write the corresponding derivative rules, what would the edges, the weights for each of these edges be? Partial derivatives. Partial or full, again, I'm just going to generically write dy over dx, because as you will see later, you're going to, the distinction between partial and full derivatives gets to be a little fuzzy, right? So each one of these is going to have dy over dxm. And then what is, if each variable x was incremented by a small delta x, right? So xi was incremented by delta xi. What would the influence of this guy be out here? Using the rule that we just had. This is going to be delta x1 times dy over dx1, right? What is the cumulative influence over here if all of them change? Yeah, but just looking at this figure, what would it be? It's going to be the sum of everything coming in over all of the edges, is it not? And so that's going to be delta y equals summation I dy over dxi delta xi, right? This notation making sense to everybody? The figure should make sense because we're going to use it. And just in case you don't get it, you're going to have them in your quiz, right? So here's what the figure looks like. And so I can write out this partial derivative rule that you're all familiar with. Delta y equals the sum of the partial derivatives of y with respect to each of the variables times the corresponding increase in the variable, right? Now, using the same rule, let's say I have this situation where y is a function f of a variable which itself is a function g of x. So y equals f of g of x, right? So how can I draw the influences over here? X influences y, f, x influences g, and g influences y. Everyone clear? Right. So now using the same rules, what are the derivatives going to be? What are the weights of these edges? What is the weight of this edge? dg over dx. What about this guy? dy over dg, right? And so here, I have x, g, y. So this is dg over dx, dy over dg. If I have a small increment delta x over here, what is the resulting delta g? This is going to be dg over dx times delta x, right? This is delta g. And what is the corresponding dy, delta y?
dy by dg times delta g.
So, so I'm going to have delta y equals dy over dg times delta g, correct? Which in turn is going to be dy over dg times dg over dx, delta x. So again, we're all familiar with this rule, but you can see how this actually gives you the chain rule, right? Just drawing these pictures out. Pictures are very nice things. But what this is telling you is that a small perturbation of x is going to result in a small perturbation of g, and dg over dx tells you what this, how this perturbation scales. Similarly, a small perturbation of g results in a corresponding perturbation of y. So you can chain these. You can say a small perturbation of x results in the small perturbation of g, which in turn results in the small perturbation of y. So that's where the chain rule comes from. Now, and so voila, here's the chain rule that you're all familiar with. Now, suppose I have something of this kind. I have y equals f of many different functions of x. So for example, y equals some function of cos x, sin x, and tan x, right? How would you draw the influences over here?
So we'll differentiate one and multiply the other.
I'm asking the influence, yeah.
Each x will
G1 to GM.
Thank you, beautiful, right? So I can say x, g1 to gm, right? And each of them is going to influence y. Everyone with me? What are the weights of these edges?
Partial derivative.
Partial derivatives. Okay, so this one is going to be what? Is this a partial derivative over here? That's a full derivative, right? Because g is dependent on only one variable, correct? And so this is going to be dg1 over dx. What about this one? dgm over dx. What is the weight here? Partial of y over gm, right? Partial of y over g1, and so on for every one of these edges, right? So everyone with me, is this figure making sense to all of you guys? From this, now can you tell me what is the derivative of y with respect to x? The figure should tell you, right? Yes.
Sum of basically from 1 to m.
Yeah.
Yeah, partial y over partial g1 or gi, sorry.
Times delta gi, right?
Yeah.
Which I can write it as I equals 1 to m partial y over partial gi. But then delta gi is simply delta x times dgi over dx, right? And so voila, that is your derivative of y with respect to x. Again, is the figure making sense? And how it actually explains how perturbations influence each other and how all of this builds up into a cumulative derivative, right? And so basically what we have here as the situation here, we say, I can just say zi equals, gi of x, that's just for notational simplicity. This is what it looks like. So any small perturbation of x is going to result in perturbations of all of these guys. Each one of these perturbations in turn is going to influence y. And so the whole thing, regardless of the complexity of the function itself, the influences are incremental, they are summed. Okay? And so that's how we end up with this chain, with this distributed chain rule for nested functions of many functions, right? Or functions of many nests, whatever. So now, for any nested function, L equals f of y, summary, dl over dz is dl over dy times dy over dz, right? And for L equals f of z1 through zm, where zi in turn is some function gi of x, the rule says that dl over dx is the sum over all of these guys of dl over dg times dg over dx, right? Okay. So any questions? We're going to keep revisiting these for the next few classes. So I hope we have no questions. So now let's go back to the problem that we actually started off addressing. How do I compute the derivative of the loss, the divergence, between the actual output of the network and the desired output of the network with respect to any parameter in the network? This is the problem we actually wanted to solve, right? And before that, you have 2 polls on Piazza. Are those released? Perfect. Tell me when 45 seconds are. much time to go.
You said if the poll is closed.
Pardon me?
Since the poll is closed for me.
Those are on Piazza. They're poll 1 and 2. Yeah.
It said it's closed.
It said it's closed.
Anyone did it on platform?
I think you should refresh it. It's all right. Okay, your time's up, guys. We have alarms. Let's go on. Does anybody want to tell me the answer to the first question? True or false? True. Can I hear it aloud from everybody? 1, 2, 3. True. Thank you. That's how I keep you awake. What about the second one? Both are right? Okay. So anybody who doesn't believe the second one, these answers? Both are right, yeah? Okay. So now let's go back to our problem. I'm going to show you, use this tiny little example graph just to, for the purposes of illustration, to show you how the math works. So this is a network with how many layers? 2? 3 layers, right? 2 hidden layers and an output layer. Each layer has 2 neurons. But if you look within each neuron, this is what each neuron looks like. There are 2 steps of computation. First, you compute an affine function of all the inputs. Then you pass that affine value through an activation. Now, just for completeness sake, I've also added this extra 1 to account for the bias, right? And so now, if I look into this carefully, I would have all of these parameters. Every neuron and every layer is going to have a bunch of incoming weights, and a bias, which in this particular example is simply subsumed by the weight coming out from the single fixed value of 1 at the bottom, right? Now, but we've already seen how to label the parameters. Let me introduce a few more variables. I'm going to call the affine value that results from the affine function of inputs at each variable, at each neuron, by the symbol z. So z1 superscript 1 means that this is the affine value computed at the first neuron of the first layer. So also this one here is the affine value computed at the second neuron of the second layer, and so on, right? Now, that's the affine value that goes in through the activation, and then you get an output of the neuron. I'm representing the outputs of neurons by the symbol y. So again, y subscript 2 superscript 2 in parentheses means that it is the output of post-activation output of the second neuron of the second layer. Any questions? No, okay. So the output of the network finally goes through a divergence function, which compares the output to the target output when you're performing any training. And so what we really want to know is what is the derivative of the divergence with respect to the various network parameters. Now, to compute this, the derivative of this divergence with respect to, say, this term over here, remember, we are really computing a chain of influences. So the question we're asking is, how much does a small perturbation of this guy change this guy, right? So in order to do that, you have to sort of work your way up. How much does a small perturbation of this one affect this? How much does a small perturbation of that affect this? And so on, all the way to the network out to the end. But then here's the thing. We know that these derivatives depend on where you compute the derivative, which means that we need all the intermediate values in the network too. So you need to know, in order to know how much what the derivative of the divergence with respect to this W is for this particular input, you need to know these Z's and Y's for every neuron of the network. So in order to compute the derivative, the first thing we will do is to pass the input through the network. So for any input, you have the X, you have the desired output, D. You're going to pass D through the network and compute the actual output Y. And then you would compute the divergence between the two. and then you're going to compute the derivative going backwards. So this process of computing the output from the input is what is normally referred to as the forward pass. It's the forward pass because you're passing the input forward through the network. And so just for notation's simplicity of notation, I'm going to call the input the output of the 0th layer. Again, I can just, so that I don't need to have multiple symbols. So y superscript 0 represents the input. And in this particular illustration, I'm not going to have a explicit bias. You're going to assume that one of the weights represents the bias, right? So let's see how this arithmetic works. Yeah.
I have a question. Does the bias need to be the same across one layer?
No.
Okay.
So take a look, right? If so for example, I have W02 out here, and this is W01, right?
Oh, I see.
They're different symbols, right? Yeah. So here's what we would do. You give the network, you're going to initialize the network, or the network has its current set of parameters, W, right? So at the very first neuron of the first layer, the affine value is simply going to be the weighted sum of all of the inputs, right? So I can say Zi1 is the affine value Z at the first neuron of the first layer is the weighted sum over all the inputs over I of Wi1, which is the weights of the ith input to the first neuron in the first layer, times yi0, which is just the ith component of the input, right? That gives me the affine value of the first neuron. Just generalizing that, I can replace the 1 over here that I had by the symbol J, and I can correspondingly compute the affine values for all the neurons in the first layer. Once I have done that, what will the next step be? So that gives me all the intermediate values at the location shown by the arrow on top. The next step is all of these are going to be passed through the activation functions. So you're going to get next that yj1, which is the output of the jth neuron in the first layer, is simply the activation function that works on the first layer applied to the jth affine value to the first layer, right? So I have now computed the output of the first layer, right? But then I can repeat the same process. Now I can use the same equation, take a step forward, and compute the affine values for all the neurons in the second layer. And then once I have done that, I can compute the outputs of all the neurons in the second layer by simply applying the activation function to these affine terms, and so on, all the way till the end, till I eventually compute the output of the final layer of the network. So this is my forward pass. At this point, I have computed the output of the network. So any questions about this? Here is a very simple pseudocode for it. You'll be looping in through the layers, and within each layer, you're going in from the first layer to the last. Then within each layer, you're going across all the neurons. And for each neuron, you first compute the affine value, and then you put the affine value through the activation function to get the output activation. And so now, and when you're done with this little loop, you're going to get the output of the network. Questions? Nothing particularly complicated, right? Yes.
Can the activation function among different layers be different?
Yeah, we are not putting any restrictions. They will be different. At least the final layer's activation is generally going to be different from the other layers, right? So pseudocode, here's what the pseudocode is going to look like. I'm going to just, the 0th layer output is said to be the input. You're looping through the layers. Within each layer, you're looping over all the neurons. At each neuron, you're first computing the affine value, and then you're putting the affine value through the activation function, and that's going to give you the output of the network. So far, so good. The forward pass is done. What we really want to do is to compute derivatives, right? Now, to compute derivatives, you're going to go back and look at this. When you look at the network, it's a very deep chain of influences. So you're going to have something like W influences Z1, influences Y1, influences Z2, influences Y2, influences your loss, right? So when you look at this, I want to find out how much does a small perturbation over here perturb this guy. But since you always have to compute it at the current location, the way you would have to do it is to say, how much does a small perturbation of this guy perturb the loss, right? And then take a step back. How much does a small perturbation of this guy perturb this guy? Because once I have that, then I can chain the two and find out how much a perturbation of this perturbs the loss, right? Then I have to go back here and say, how much does a small perturbation of this term here perturb this one? Because I have already worked out the dependence between this guy and the loss. So the derivative computation has to go backwards from the output to the parameter with respect to which you're computing the derivatives. It cannot go forward because you have no idea which way it's going, right? And so here's what we would be doing. Yes?
Is there any special case where we have to initialize bias with some random values? Or what happens if we initialize bias with some random values?
You always initialize the bias with the random value. See, in this particular representation, I've subsumed the bias into the weight that goes into the 1, and that weight would be randomly initialized. So anyway, so you'd be computing the divergence first. Then you'd compute the derivative of the divergence with respect to the output of the network. So that tells you, guys at the back, please shut your laptops. Again, I'll wait till you all shut your laptops. Those are the rules of this class, right? You open them when the polls are put up. And if you must work on your laptop, I won't stop you, just go outside. Right? You don't do it in the class. Okay. So going by the same rules, first you figure out how much a perturbation of the output of the network computes the loss. So you compute the derivative of the divergence with respect to the output of the network. Then take a step back. How much does a perturbation of the affine value perturb the output of the perturb the loss? And then using that, you're going to work your way back and say, what is the derivative with respect to these z values? And then back, what is the derivative with respect to these y values? And so on. You sort of compute all of the derivatives going backward, because that's how when you have the chain of influences is forward, but when you want to compute the derivatives, you have to work your way backwards. So this is basically what we're going to do. This is why we call this the backward pass. And this computes the gradient of the loss with respect to all the parameters of the network. So let's actually see the math. Now, here it is again. The network with all of the intermediate variables that we have already computed. And we already currently have a setting for all of the parameters. We have computed the output of the network, and we have computed the loss, right? So the first thing, remember, we assume that the divergence function is differentiable. So therefore, we haven't specified what the divergence function is. You can have different kinds of divergence functions. But regardless of what it is, you will be able to compute the derivative of the divergence with respect to the output of the network. So this is easy. We assume it's given or we assume we know how to compute it based on the divergence function. Now this is this is a pretty complicated can of worms. I'm just hiding a lot out here for now, because most of the divergence functions that we will work with are fairly simple. Now, going back, the chain rule, right? For any function of this kind, where L equals f of y, where y in terms of some g of z, you know that the derivative of the L with respect to z is dl over dy times dy over dz, right? So that applies here. Using that chain rule, this loss is a function of z through y. And so the derivative of the loss with respect to z is going to be the derivative of the loss with respect to y times the derivative of y with respect to z. Simple chain rule. And what is this derivative of? Now, this term over here, the derivative of the loss with respect to y has already been computed in the first step. We just assumed it was known. And so the term that we need is the second one, the derivative of y with respect to z. What is that?
differentiation of the activation function.
That's just the derivative of the activation function computed at the specific z value. So this guy, I can just write this as the derivative of the activation at the location z that was computed in the forward pass. Again, remember the derivative depends on where you're computing the derivative, so you need to know the z. And so I can just replace that with f prime of z, right? So everyone with me so far? We've just gone back one step, yes.
We need to do the forward pass first because we can only compute the derivative at the point.
Exactly.
What the point actually is.
You need to know where you're computing the derivative, otherwise you have no idea what you're computing, right? So, and then having done this, we now want to compute the derivative, say, with respect to this weight. So the weight of this edge. Now this is easy again. It's using the same chain rule. The derivative of the divergence with respect to this weight is the derivative of the divergence with respect to the z times the derivative of z with respect to the weight, right? And what is the derivative of z with respect to the weight? Because z is simply summation wi yi, right? So the derivative with respect to any wi is just
Partial derivative.
y. Yes. So this term over here is already known. We just computed it going backwards. This is simply the input to the specific edge whose weights we are computing derivatives for. So the derivative of the loss with respect to any weight is simply the derivative of the loss with respect to the output of the weight times the input of the connection that carries that weight. So everyone with me so far? Nothing complicated, right? It's very straightforward. And this y, of course, was computed in the forward pass. Once again, this is why we need the y's. So good. So I've written this. What is the next thing you need to compute derivatives for? The previous y's, right? And so let's see how we would do that. Now, if you look at, so this rule I can use to compute the derivatives for all of the weights in this layer, right? Now, to go back to figure out how to compute derivatives with respect to the y's, now we have to go back to the distributed chain rule. So if you have something of this kind where a single x influences many g's which influence an L, then we know that the derivative of L with respect to x must sum over all the paths from x to L, right? And so if I consider the derivative of the loss with respect to, say, this y, this has two outgoing paths which go into L, into the loss, and so I must sum over all outgoing paths. And so therefore, this derivative over here of the divergence with respect to y is the derivative of the divergence with respect to this z times the derivative of the z with respect to y plus the derivative of the divergence with respect to this z times the derivative of z with respect to y. Make sense? Right? Okay. And which of these terms do we already have? Someone at the back. Which of these terms do we already have? Can I hear someone's voice?
Both the y's.
Both the?
Y's.
So I'm speaking of this equation out here, right? I'm computing the derivative with respect to y. That's giving me this, right? Of these, I already have this term going backwards, right? What remains? The derivative of z with respect to y. What is that? Anyone? That's just going to be the weight, right? So because zj equals yi times wij plus a whole bunch of other things. And so the derivative of zj with respect to yi is simply going to be wij for that particular layer. And so that's going to be your derivative of the divergence with respect to that particular y. And I can generalize this to all the y's in the layer, right? So the derivative of the divergence with respect to the ith output of the ith neuron in the n-1th layer is the sum over all of the neurons in the nth layer of the weight from the ith layer times the to the neuron times the derivative of the loss with respect to the z value at that neuron, right? So is this clear to everybody? Okay, what would be the next thing you compute? Pardon me? Take a step backwards, correct? So we're going to next we're going to compute the derivatives with respect to these guys. And again, the chain rule applies. It's very straightforward. The derivative of the divergence with respect to any z is simply going to be the derivative of the divergence with respect to the corresponding y times the derivative of the activation function itself. And so you have the derivatives with respect to the z's. And then once these are done, what would you compute next? We need the weights, right? What is the derivative with respect to any of these weights? It's going to be the derivative with respect to z times the input to the weight, right? Again, the math is kind of boring. It's not complicated. It's very straightforward. And it's annoyingly simple, but I have to go through it. And so, yes?
So for like activations that are sub-differentiable or something like that, like how do you handle it in this case? Like if
We'll get to that. We'll cover all of those, right? And so then once with those, I can compute the derivative out here and keep working my way backwards. And in fact, eventually, I can not only compute the derivatives with respect to all the intermediate values of the network and all the parameters of the network, I can even tell you the derivative with respect to the input to the network, which tells me how much will a small perturbation of this input affect the loss. And that's a value that we use in some situations. So we can work our way all the way back to the beginning, right? And you're going back from the end. So here is the pseudocode for the whole computation. You would initially compute the derivative of the divergence with respect to the output of the network. Then from there, you compute the derivative of the divergence with respect to the affine values at the output layer. And then from there, you can keep going backwards. The derivative of the divergence with respect to the previous layer outputs is a weighted sum of the derivatives of the divergence with respect to the affine values of the next layer, right? And then the derivative of the divergence with respect to the affine value is simply the derivative of the divergence with respect to y times the derivative of the activation. And in between, you get also, it sort of falls off the side. You compute the derivatives with respect to the weights, where the derivative with respect to any weight is going to be the product of the derivative with respect to the output of the connection times the input to the connection. So if you write the pseudocode, it looks kind of interesting. Here's what it looks like. So this is just what happens at the output layer. But then further down, observe what happens. The derivative of the divergence with respect to any y is a weighted sum of the derivatives with respect to the y's at the next layer, z's at the next layer, right? Similarly, the derivative of the divergence with respect to any z is the derivative of the divergence with respect to y times the derivative of the activation function. Does anybody see the similarity between this and the forward pass? It's essentially the same as the forward pass. It's like flipping your network backwards and doing things slightly differently, right? Left. So it's very analogous to the forward pass. First, in the forward pass, in the first step, you computed a weighted sum of the outputs of the previous layer. Then you put it through an activation, right? Here, you compute a weighted sum of the derivatives of the next layer, and then you put it through the derivative of the activation function. So it's, in fact, you could use the same code with small tweaks going forward and backwards. So just in case you don't believe me, instead of writing this dy over dx notation, I have a simplified notation where I put a superscript of a dot in order to show the derivative of the derivative. So this one here, z dot is the derivative of the loss with respect to z. Y dot is the derivative of the loss with respect to y. And you can see that this looks just like what we'd have in the forward pass. So here was the forward pass computation. And each layer you first computed a weighted sum of the outputs of the previous layer and then put it through the activation. Here is the backward pass. You compute a weighted sum of the derivatives at the next layer and then put it through the derivative of the activation function. So the forward and backward passes look very similar in the computation. So here's your second poll. You have your clock. Okay, this is a short one. You guys done? I think everybody's done. All right. Which one's the right answer? The third? How many of you think the first is right? The second? The third? Okay, I'm glad. There are some people who don't think anything is right, but you haven't raised your hands. Okay. So clearly, backpropagation is used to compute the derivatives of the divergence with respect to model parameters. Backpropagation is not the process of training the network. Backpropagation is the algorithm that is used to propagate derivatives backwards through the network to compute the derivatives of the loss with respect to various parameters. These are used later in the gradient descent algorithm in order to train your network. So backpropagation is not used to update model parameters. Its sole purpose is to compute derivatives, right? So those are the simple cases. Now, we're going to look at some special cases. So far, we've assumed that the computation of one neuron does not affect the output of the next neuron. But we saw some cases where this was not necessarily the situation. Anybody remember what that was?
Rationalization.
You're going way ahead, man. So we call this a kind of activation. What did I call it? Softmax was an instance of vector activations. Thank you, right? This is only the 5th class. I expect you guys to keep track. By the 15th class, I can understand you've given up on me, but not so soon, right? So we had vector activations where you had a function acting jointly on all the inputs and jointly computing all the outputs. And how did this differ from just a collection of scalar activations? Anyone? What was yes?
Well, now the like derivatives are going to depend on other.
Absolutely, right? So because over here, in this case, if I perturb this input, this is the only one that gets perturbed. Over here, if I perturb this input, all of the outputs are going to get perturbed. And conversely, any perturbation over here can be attributed to all of these guys. So there's a difference. Now, in scalar activations, every z only influences the corresponding y. And so when I said I'd have yk equals f of zk, in the vector activation case, you had the set of z's, which I could represent as a vector, collectively being operated on by a function f to collectively compute this vector y. So now a vector goes in and the vector comes out. Modifying any component of the input vector is going to modify all output vector components. And any perturbation of an output vector component can be attributed to all input components, right? And so if I want to draw the influences, here's what the influence diagram looks like. In the scalar activation case, each z influences only that corresponding y. In the vector activation case, every z influences every y. Do you see the distinction? And once you see the distinction, you can also see how this changes your derivatives, right? So here, when I have the scalar activation, the derivative of the divergence with respect to z is simply going to be the derivative of the divergence with respect to y times f prime of that particular activation, right? On the other hand, if I have a vector activation, then a perturbation of any z is going to perturb all of the y's. And therefore, if I want to compute the derivative of y with respect to any particular z, of the loss with respect to any particular z, I have to consider all outgoing paths from that z. And so in this case, the derivative of the divergence with respect to any particular z is going to be the sum over all of these y's of the derivative of the divergence with respect to the y times the derivative of y with respect to z. Is that making sense? Right? And so it's a fundamental difference. Now, the special case here was the softmax. Now, in the case of the softmax, here's what we had. Each y was computed by exponentiating the corresponding z, but then normalizing so that the y's sum to 1. Now, what happens here? If I increment this z, what happens to this y? Does it go up or go down? Can I hear? Okay. I want everybody to yell the answer out because this is how if I increment that z, does y go up or down?
Up.
Okay, so what if I increment this other z over here? This guy? Down, right? So what will the sign of the derivative of y with respect to the z on top be?
Positive.
What about the remaining z's?
Negative.
Negative. And that's how it must work, right? Intuitively, that's how it's got to be. And so if you actually work out the arithmetic, which the derivative of the divergence with respect to any z is going to be, the sum over all y's of d div over dy times dy over dz. And the derivative of y with respect to any z, we sort of saw this formula in the last class. I'm not going to bore you by working it out, but you should be able to look at the formula and tell me it kind of makes sense. Why so? Because look at this. Y is a value that's always between 0 and 1, right? And so is this top term positive or negative? It's always positive, right? So what term am I? So that is the derivative of the through term, right? The derivative of the y with respect to each its corresponding z. What about the second term? Is it positive or negative? Negative. It's always negative. So it's the derivative of the cross term. Incrementing some other z is going to decrease this y. And so the overall derivative of the divergence with respect to any z can be written as a summation over all y's of the derivative of the divergence with respect to y times, it just works out like so, the corresponding y times, this is a Kronecker delta. It equals 1 if I equals j and 0 otherwise. This is just for notation, times Kronecker delta minus yi. So, but again, formulae apart, you get the idea, right? You have to sum over all incoming terms. And also how the derivative works in this case. So typically, in a neural network, the output layer is a softmax layer. So somebody asked, can different layers have different activations? We actually do have different activations in different layers. At least the output layer is going to have a different kind of activation. And so if you were to write the pseudocode over here, for the output layer alone, I actually have the proper, when I'm computing the derivative going back with respect to any affine value, I'm summing over all of the output terms in that layer. And anyway, so we looked at one special case, which was vector activations. Let's look at a couple more special cases. There are a few others in the slides. They will appear in the quiz. But let's look at non-differentiable activations. Now, one of the requirements we had for the activations was that the activations must be continuous. Does it mean that they will always be differentiable? Can you give me an example of an activation that's continuous but not differentiable? The ReLU, right? Is it really not differentiable?
It is differentiable when c is greater than 0, but at 0 it's
Only at 0. So these are typically not differentiable at very isolated points. The odds that you're going to hit that point are very small, right? Nonetheless, we must consider them. So in these cases, the ReLU looks like so. And where did I keep my sword? I need to defend myself against the board. Okay. So this is what the ReLU looks like. Out here, the slope is 1. Out here, the slope is 0. At this location, the slope is undefined, right? So how do you compute the derivative at that particular point? Now, the way the mathematicians like to explain it to you is through something called a subderivative or a subgradient. But the problem is when you think about things this way, it gets to be a little, there are rules and rules, and they apply to this very specific kinds of functions. But the general idea is this. What was the direction in which we wanted to move our parameter in order to decrease the loss? We wanted to move it in a direction that decreased the loss, right? That's why we went against the derivative. And the derivative was the one direction where you could move it against that direction and decrease the loss, right? It was unique when the function was continuous. But then when you have non-differentiable points like this, you just want to find any term v such that moving in the direction of v is going to decrease the loss. And so you can sort of draw lines of this kind, as you can see, and any line that touches the curve but doesn't intersect it has a slope such that when you go against the slope, the function value decreases. So these are all subderivatives at this point. But then there's a better way of thinking about it. You can think about it as the function. So if I have a ReLU, and the ReLU is like so until 0, and after 0, it's at that angle, right? You can think of the function as instantaneously turning from a slope of 0 to a slope of 1. So what is the actual slope of the function at that corner? Any one of these slopes will do, right? Because this entire turning from a slope of 0 to a slope of 1 happens at one location. And so any one of these slopes is a perfectly valid answer to be using. And so the subderivative over here, it's not strictly, it doesn't follow the strict definition of subderivative, but for our purposes, it's enough to think of it this way. You can think of the function as rotating smoothly from a slope of 0 to a slope of 1 instantaneously, and any slope, any value between 0 and 1 is a valid derivative at that point. And so you can think of it, you can also look at it this way. If I actually plotted the derivative of the function with respect to z, the derivative is 0 until here. And when you go beyond 0, the derivative is 0 on the negative side of the line. It's 1 on the positive side of the line. Anything between those two limits is a valid value to use over there, because you can think of the function as just turning from a derivative of 0 to a derivative of slope of 0 to a slope of 1, right? And so the typical value that we will use is to say that if the derivative of this function is 0 for negative values, and it's 1 for non-negative values, even at 0, because that's a valid answer. Does that make sense to all of you, right? Okay, yeah.
So what is, as you said that any slope between 0 and 1 is good, what is generally used then?
We use 1. We use 0. At 0, we use 1.
Okay.
Because we want it to decrease fast, that's all.
Okay, so 1.
You're not going to encounter that particular point very frequently, though. So you can write anything and you'll never see it. Now here's another activation function. It is the max. You get a collection of inputs and you output a single value. And the specific value that you output is just the maximum value. Now, as it turns out, this max is actually a very special case of the ReLU, believe it or not, but we won't go into why. But let's think of it this way, right? If I have a collection of values, z1 through zn, and y is simply the maximum of these, what is the derivative of y with respect to all the z's?
One with that.
So here's how we think about it. How did we define a derivative? The derivative said, the derivative gave us how much the output of the function would change in response to a small perturbation of the input, right? So suppose I have x1, x2, x3, and the maximum is x3. So y equals x3. Now, will perturbing x1 change y? Yes or no?
Can change if it goes beyond X.
A minuscule perturbation, right?
Minuscule can make X.
How much? If the difference is not 0, I can always make the derivatives, the difference smaller, right? For an infinitesimal perturbation of x1, will y change? No. What about x2? So what is the derivative of you're sleeping? You want to go wash your face? No. Be very afraid. I come up here sometimes. Right. So what is the derivative of y with respect to x1 going to be in this case? 0. What about x2?
0.
What about x3? Go ahead. Why?
Because y is equal to x3.
So any small perturbation of x3 is immediately going to show up as
Equivalent perturbation.
the equivalent perturbation of y. And so the slope is going to be 1. Now, getting to the case where both x2 and x3 are equal and equal to the max, then what is the derivative going to be? Perturbing either is going to increase y, right? So as far as you're concerned, the derivative with respect to both is 1. So any questions? Yes, no? There's a poll. Time. I like the beep. Okay. All right. So let's shut this. Is the first statement true?
No.
Second?
Yes.
Third?
No.
Fourth?
Yes.
Fifth? Thank you. Right? And the sixth is no. I missed that. Okay. So going back to our backward computations, in the backward pass, these derivatives of activation functions could be subderivatives. And as it turns out, the specific, yes.
I have a question about the subgradients. So if there's like you said, the 0-1 case where you can pick anything basically between the limits. So if there are functions where the derivatives also depend on the variable, like for z and z square or something like that.
Yeah.
Then do you just calculate the value at that point and then interpolate like?
So let me give you an example, right? Wait, I need a third board. So we actually had an example on the slides. Suppose I have a function of this kind. So at this point and at this point, the behavior is going to be very different, right? So the slope here is let's say it's 0, let's say it's alpha, let's say it's beta over here. At this location, what are the subderivatives that are acceptable?
0 to alpha.
And over here,
Alpha to beta.
alpha to beta, right? Because the function is curving from alpha to beta. So it depends on the function. So overall approach, here's what we have. For each data instance, in the forward pass, you pass the instance forward through the net. You store all intermediate values of the computation. Then in the backward pass, we sweep backwards through the net, iteratively compute all derivatives with respect to weights. That's for one instance, right? But the actual loss is the sum of the divergence over all training instances. So therefore, the derivative of the loss with respect to the parameters is going to be the average of the derivatives with respect to average of the derivatives for all of the training instances. And it is this average that actually gets applied in your gradient descent, right? Questions? No. So training by backprop. If you're given a collection of training instances, you initialize all the weights, all the parameters. Then you go through your gradient descent iterations where first you perform a forward pass where you pass each instance through the network. You aggregate the loss. You compute all the intermediate parameters, intermediate values. Then for each instance, you perform a backward pass, compute the derivatives, aggregate the derivatives, and then update the parameters, and then repeat and go back to the next step of the gradient descent update. So within each iteration of the gradient descent update, you have to go over all the training instances to compute the average derivative, and then update the parameters using the average derivative. Now this is important. The actual loss that you're minimizing is the average over all training instances. So the derivative must also be averaged over all training instances in principle. And this is an issue that we will deal with in some depth in a couple of classes. So that was the basic idea. Now, any questions? That's the kind of math that's very simple to understand, but we're not going to use it.
Can you re-explain the average derivative for the loss?
The loss is the average divergence for all the training instances, right? That's right. So, or the average of the losses for all the training instances. So now, was there any confusion about how we did it? You should be able to derive this in your sleep, right? There was nothing complicated. It's very straightforward. A bunch of multiplications and summations. And if I woke you up at midnight and, gave you the...
Probably not.
Yes. But anyway, it turns out it can be even simpler. It can be much, much simpler if you are willing to believe me. So there's a certain degree of faith over here because almost everybody that comes to this class swoons when they first see a vector, and then worse when they see a matrix. And then when you take a derivative with respect to that vector or matrix, you just quit the class. But anyway, but if you just believe me, this is easy. For layered networks, it's much simpler to think of the process in terms of vector operations rather than scalar operations. The arithmetic is much simpler. And even more importantly, you use GPUs, you use fast matrix libraries, so they make things even faster to compute. There's no way in, you would ever actually write a practical piece of code that looked like this unless you were me 30 years ago. Because I was stupid, but then we've learned a lot since. This is how you do it. You like to restate the whole thing in terms of vectors and matrices. How so? Think of this. So let's say this is the set of neurons at the output of the k-1th layer, and you want to see what's happening at the kth layer. So let me arrange all of the outputs of the neurons in any layer as a vector, as a column vector. So also, let me arrange the affine values at the input to the activations in any layer also as a column vector. Now, I can arrange all the weights as a matrix. So, for example, if I have say the ith neuron here, or the jth neuron here, and I equals 0 to whatever, m in the previous layer, I have all of these weights coming in, right? This is W1j, W2j. So these are all the weights coming in to the jth neuron in the next layer. So I'm going to write all of these weights as a row in the matrix. it's 1J, and so on. So I'd have one such row for every one of my neurons over here. And so if I have, say, 10 neurons in one layer and 5 neurons in the next layer, each neuron in the next layer is going to get one row of my weight matrix with 10 elements. And so I'm going to have a 5 cross 10 weight matrix, right? So if I write things similarly, I can write the biases for all of these neurons as a vector. So I'm just basically writing all the biases of the neurons out in the same order as the neurons itself. And now when I write things like so, then this forward pass equation that we wrote, which looked really ugly, ends up being very simple. It's just a simple matrix vector operation. And so as a result, because of this, if you look at how we wrote out the weights in the weight matrix, so I have, say, y1, y2, ym in the k minus 1th layer. I'm writing this as the vector yk, except the k is now the subscript. So this is yk. Similarly, I had, so this is yk minus 1, sorry. And I had zk equals z1 of k to whatever z L of k. These are my z values, also written as a vector. And so you can just see that if I multiply this guy with, say, W11, W21, W31, WM1, W12, W22, WM2, and so on, and then add to this B1 of k through BL of k, this should just give me the zk. You can just check out the arithmetic. It's all the weights times the y values, right? So y1 over here multiplies W11. So the first entry, first column, is always going to be the weights from the first neuron. The second column is going to be the weights from the second neuron, and so on. So once I write it in this manner, then it's very easy for me to just say that zk equals wk times yk minus 1 plus bk. Is this making sense to everybody? Right? We're going to use it. And for the activation, now I can just write everything as a vector activation. So yk is some activation function applied to zk. So when I write things in this manner, then the forward pass becomes absurdly simple, right? Your initial input is y0, and then your first affine value is simply W1 is just the matrix of weights for the first layer. I can simplify the notation, it's W subscript 1. So the affine values of the first layer are just W subscript 1 times y0 plus B1. B1 are the biases for the first layer. And then, of course, the y's are just the activation function applied to the z values. And so I can just keep doing this. Z2 is W2 times y1 plus B2. And y2 is f of z2. And so on, all the way to the end. Now you'll observe over here that I've also written this funky looking equation over here. What is it actually telling you? It's also telling you that when you look at it in this manner, the neural network is actually a very nested function. You have the inputs, then you have the first affine transform being applied to the inputs, then you have an activation function applied to the affine transform, then you have an affine transform applied to that output, then you have another activation applied to it. So it's just a nesting of many activations and affine transforms. But regardless, the actual code for the forward pass becomes so simple. I just set y0 as the input, and then I go through the layers, and in each layer, I first compute my affine value, and then compute the activation value itself. And the activation value for the final layer is the output of the network. And so when I write it in this manner, because I'm treating every layer as a vector activation, the distinction you have to make between scalar and vector activations also sort of disappears in the notation. So the forward pass code, which was big and ugly earlier, becomes a much simpler code. Where do you think the grief comes in? So that's where I'm going to leave you hanging because we're at the end of the class. But it's about understanding derivatives. You haven't yet swooned, right? I'm leaving that for tomorrow. We'll have I'm going to announce an extra hour tomorrow just to complete the rest of this lecture. If you can't make it, I understand, but I highly recommend that you do. And you must watch the video because it's going to show up in the quiz. Thank you.